We have encountered equilibrium in the past, but now since we have learned torques, we're expanding our definition of equilibrium. So here's an example. Let's define the equilibrium first before we do the example. So the equilibrium we had was net force is equal to 0. So this includes net force X and net force Y or net force Z in any all objects equal to 0. Right, so that is for a translational equilibrium. Now that we have torques, we need to enforce torque net equal to 0. This is for rotational equilibrium. So when an object is in an equilibrium, there's no force, no net force acting on it, no net torque acting on it, and this will allow the object to either stay stationary without rotation, or it could be rotating at a constant speed. It could be translating at a constant linear velocity. It could be doing both as constant linear and angular velocities. But we're more interested in static equilibrium. So if we add static equilibrium, we also want to say that velocity is equal to 0, so is angular velocity. So the objects will just stay stationary. So let's do an example. We have on top we have a 0.12 kilogram horizontal meter stick. Meter stick has several weights attached to it. So 0.1 kilogram at 0.1 meter. So that's this one here is 0.1 kilo. And this location is 0.1 meters. And then 0.05 kilograms at 0.4 meters. So this is 0.05 kilograms. This is 0.4 meters. And then a 0.15 kilogram at 0.6. So 0.15 kilogram at 0.6 meters, and then lastly a 0.065 kilogram at 0.8 meters. So this is 0.065 kilograms at 0.8 meters. So besides all these weights, we also have the meter stick, which is 120 grams, right? So this meter stick, uniform meter stick, has this 120 grams. So this is a 0.12, and it should be at 0.5 meters. We don't know where the fulcrum is, but let's take a brief look. There's a 0.1 gram over here, or 0.065. So that probably will tip the meter stick toward the left. But then you added some more weights. So I'm not sure where the fulcrum has to be. So I'll just pick an arbitrary location here and put the fulcrum here. I'll call this location X. Right here, X. Alright, so that's where the fulcrum is. And next we can calculate the net force and net torques. Because we're more interested in the torques, we'll start with the torques, and we'll pick an axis of rotation. And it is easiest if you pick the axis of rotation at the fulcrum, so where X is fulcrum. Alright, so then we can find out the lever arms. So we'll give some numbers. So this is mass 1, mass 2, mass 3, mass 4, and this is mass of the meter stick. So mm. So how about this? Mm. This is m1, m2, m3, and m4. Alright. So then lever arm 1, that is between where mass 1 and X is. So, well, this is 0.1, right? So if you subtract 0.1 out of X, you'll get the distance. This is actually regardless where this fulcrum X is. So X minus 0.1. So if you're on this side, for some reason the fulcrum's on this side, it's not possible. But if it's on this side, then x minus 0.1 becomes negative, and that actually gives you a correct direction for the torque. So let's just use this is equal to x minus 0.1, and L2 is equal to x minus 0.4. And that will be this tiny distance. It doesn't really matter if the fulcrum is actually on the other side. If it's on the other side, it becomes a negative quantity, and that apparently acts against the fulcrum. So then L of the meter stick is x minus 0.5. So this transitions into a negative. And then L of mass 3 is x minus 0.6. Again negative, I suppose. L4 is x minus 0.8. Okay, so now we have all the lever arms, and the forces are all just m times g. So the torques, so the torque T1, tau1 is equal to m1g x minus 0.1, and then torque 2 is equal to m2g x minus 0.4. Then torque 3 is torque meter stick is equal to m meter stick g x minus 0.5. Then torque 3 is equal to m3g x minus 0.6. Then torque 4 is m4g x minus 0.8. Okay, so we'll just sum up all the torques. So net torque is equal to all of these. I'll plug in the numbers. So the first one is 0.1, and I'll also factor out all the g's. X minus 0.1 plus the second mass is 0.05, x minus 0.4, and then the meter stick 0.12, x minus 0.5. Then third mass 0.15, x minus 0.6. Then last mass 0.065, x minus 0.8. So all of these multiplied by g, and torque is equal to 0. And since we have no net torque, we don't have any angular acceleration, and there's also no need to calculate rotational inertia. That makes things slightly easier in that direction. So now we just need to combine all the x terms, all the constants, and try to find out what x is equal to. And this is entirely algebra. So let's see, 0.1x, 0.05x, 0.12, 0.15, 0.065. So you add them all together. And that's equal to 0.1 times 0.1, 0.05 times 0.4, 0.12 times 0.5, 0.15 times 0.6, and 0.065 times 0.8. The g has been divided out, and then you can find x is equal to 0.478 meters. All right, thanks.